Year 11, or really Year 12, Mathematical Induction, Extension 1. Okay, Part B, question B, I guess. Alright, so if you remember, there's three types of induction. The first type was summation, which is what we're doing here. The second type was divisibility, and the third type was inequalities. Yeah. Cool. So we're going to look at hopefully all three today. Summation. The formula that you want to eventually prove for a mathematical induction is S of k plus T of k plus 1. That must equal to S of k plus 1. Okay? So your S of k plus T of k plus 1 must equal to S of k plus 1. And that makes sense. Why? Your k plus 1th sum must equal to your kth sum plus the k plus 1th term, which gives you the whole k plus 1th sum. So it makes sense. You just got to do it like that. Now, mathematical induction. Okay, there's 4 steps. So you write step 1. You write test true for n equals 2. And in this case, it says greater than or equal to 1. So that first case is going to be n equals to 1. Okay? And in most cases, it is, but not all the time. Okay? So if it said even numbers, as I said, then you're going to probably test n equals to 2. If it said n is greater than or equal to 2, so as you can see for part C, you probably have to sub in 2. Okay? Yeah. Alright. Test true for n equals to 1. You just got to sub it into there. Left hand side equals to 1. 1 plus 1 equals to 2. Right? And then right hand side. If you've done it right, obviously it should equal to, because you're testing. You're not showing. So if you've done it wrong, then you're wrong. Easy as that. 1 plus 1 and then 1 plus 2. That's 3. 3 times 2 is 6. 6 divided by 3 becomes 2 as well. So 6 times a third is also 2. Therefore, true for n equals to 1. It's a proof. While we're here, we might as well do step 2. Step 2 is assume true for n equals to k. Yeah. Right? So then you've got to write the whole question now just with n is k. That's it. So nice and easy step. 1 times 2 plus 2 times 3 plus 3 times 4 plus plus k plus 1 is equal to 1/3 k plus 1 k plus 2. Any questions? No. Easy. Step 3, which is where you're actually getting your marks. Okay? You want to prove true for n equals to k plus 1. You want to prove true for n equals k plus 1. So I like to write an IE there. That's what you're trying to prove. Like I said, you're essentially trying to prove this. 1 times 2 plus 2 times 3 plus 3 times 4 plus ... Now, rather than n, it's k plus 1. So k plus 1. And then k plus 2, because k plus 1 is k plus 2, is equal to 1/3 k plus 1, then k plus 2, then k plus 3. You see that's what you're trying to prove? Yeah. Okay? But just n is k plus 1, that's it. You should already know how to do that from a lot of different substitutions. Anyways, so in other words, this part here is my S of k. Can you see S of k? Can you see it? 1 times 2, 2 times 3, 3 times 4. But can you see how the last part is a little bit different? And the reason why that is because that's your sk plus 1, but that's your S of k. And that's where the formula got derived from. Right? Okay, the proof is not hard. Here we go. Okay, so S of k. S of k is all of this. Let me write it. S of k plus T of k plus 1. S of k is always going to be this term here. Right? This term here. Because that's your sum of your kth term. Sum of your k's. Right? Plus your k plus 1th term, plus this term. And then you should hopefully eventually prove it to become this right hand side here. So here we go. Usually they like to tell you to write this, so we would do it. 1 times 2 plus 2 times 3 plus 3 times 4 plus ... plus k plus 1, k plus 2. Okay? And then that part there, all of this, plus just up to there, somewhere, is going to be k plus 1, which is equal to 1/3 k plus 1, k plus 2. 1/3 k plus 1, k plus 2. Then you're going to add on top of k plus 1, k plus 2. This extra term here. You get that? Again, you don't want a dot, dot, dot. That's the whole point of changing this assume. Okay. K plus 1, k plus 2. What do you reckon you'll do? When you get something like that, what does your instincts tell you to do? When you get something like that and look at all these are all products, what do you reckon you'll do? Yeah, that's what your gut should tell you anyways, alright? Even if I didn't say product or anything like that. You should just factorize. When you see they're the same, k plus 1, k plus 2. Hey look, k plus 1, k plus 2. Tick, tick. I'm looking for a third k plus 3 hopefully somehow. Anyways, that's a third k plus 1. Right? Okay. I'm going to times this by 3 because I can see I need a third k plus 3. So I'm like, okay, probably, and I need the third outside. So probably like this. Common denominator. And then can I just take the 3 out? Because it's all times. And I can just write the third there. And that's it. You prove it's equal to the right hand side. Can you see it?
Yeah.
Equals to a third k plus 1, k plus 2, k plus 3. You got to follow the proof. That's why I write this. So you got to follow every step you do has to follow aiming that, which equals to s of k plus 1, and you're done. Step 4. For now, I'm just going to write therefore. Actually, I'll write the full proof right now, but you don't, like I said, you don't require it usually. Therefore, okay. Therefore, it is true for n equals to k plus 1. See, it's true for n equals k plus 1. Only if it was true for, look what you did there. Look from that line to that line. What did you do there? You used the assumption. Only if it is true for n equals to k. So it is true for n equals k plus 1 only if it is true for n equals to k. But then, since it is true for what? What would you prove it's true for? What number? Since it is true for n equals to 1, therefore it is true for, let's say, n equals to 1 plus 1, which is 2. N equals to 2 plus 1, which is 3. Blah, 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 blah. So n is greater or equal to 1. True for all positive integers. True for all positive integers and by mathematical induction. That's it. Cool?
Yeah.
Okay. Let's do another question. Let's pick this one. Alright, there's one thing I want you to remind me. When we finish off induction, tell me, please, tell me, do exam questions. Because I can guarantee you. Here we go. So now we're going to do this question. Again, is it a summation question still, or a divisibility, or a inequality? Well, actually it is still a summation. You'll realize the difference between the other ones, but it is summation because you see plus. Again, there could have been a product, and I told you what the product would be. It's s of k times 2k plus 1 equals to s of, it's just common sense. The k plus 1 sum times that term should give you the sum of k plus 1s. It's common sense. All right. Step 1. What do I do? Let's see if you remember.
Test true for n equals to 1.
And then you can see. Because it's obviously, it is. If it was greater than, if it was n is greater than 1, what do you test true for? If n was greater than 1, for n is greater than 1, you test true for n equals to. If it's this, for n is greater than 1, you have to test true for n equals to 2.
2.
Because it's not equal to 1.
Yeah.
Oh, crap. n equals to. Okay, I can't write that out. Too bad. Alright, I'll just do this. N equals to 2.
Yeah.
Okay, because obviously it's greater than 1. It doesn't include 1. That's it. Alright, so you sub it into the left hand side. equals to 1. Sub it into the right hand side equals to a quarter. 1. 1 plus 1 squared. That's 2 squared. 2 squared is 4. 4 times a quarter is 1. So if you do a mistake here, you already know. If you get somehow 2, you know you're wrong because it's meant to be 1.
Yeah.
Alright, that's it. Step 2. What do I do in step 2?
Assume
Yes.
true
Yes.
for
Yes.
n equals to k.
That's it. So you rewrite out the whole question and you just substitute it for k. Not hard. Step 3. I'm proving true for.
N equals k plus 1.
That's it. So i.e. I would like to prove that 1 cubed plus 2 cubed plus k plus 1 cubed is equal to a quarter k plus 1 squared k plus 2 squared. Okay, I'm just subbing in k plus 1 where n is. Okay, well that means, here we go. We know that s of k plus t of k plus 1 must equal to, s of k is all this, so 1 cubed plus 2 cubed plus dot 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 plus k cubed, that's my s of k, plus k plus 1 third, plus k plus 1 cubed. You have to write that step before you go on to this. You can't just go to that to that. Alright, so that line must be there, and then you just substitute that whole thing for that. Because you don't want the dot dot dot. A quarter. K squared, k plus 1 squared, plus k plus 1 cubed. Any questions right now? Okay. And then can you see, again, k plus 1 squared, k plus 2 squared, but then that's not your worry. All your worry is factorization right now, because they're all times. K plus 1 squared. Okay? Then you're going to get a k squared over 4 plus k plus 1. When you times the all by 4, it's going to come like that.
Yeah.
And then look, you can take the quarter out. So that's a good step what I just did. So at least I can take my quarter out. I can get this. And this is apparently meant to be k plus 2 squared. Let's have a look. K squared plus 4k plus 4. Yes, it is. It's a perfect square.
Yeah.
You're done. You don't need to do more lines than necessary. If it makes sense, how you got there to there, that's it. Which equals to s of k plus 1. And then step 4, now I'm just going to cheat and say, therefore, true by mathematical induction. But if you just remember what I wrote. Okay, so now let's have a look at a little bit more of an advanced question. Okay, so probably the challenge question extension 1, something that will be asked towards the end of your paper. This is still part of summation, so it's not divisibility or anything. You should find this one interesting because it is the sum of your geometric. So if you go back to your series and sequence, this is your sum of geometric progression. And we're about to prove it. So here we go. Using mathematical induction. So step 1. Test. True. N equals to 1. So n is equal to 1. Do you care about the A?
No.
Do you care about the R?
No.
Ooh, imagine, you're right, right? Imagine you had this in your exam, and I'm sure, and I've seen it all my students that have had this in their exam, or they've got this, they go, what's A and R? You don't care. It's about the n's. Okay, A and R, constants.
Yeah.
So what's AR to the power of 0? What's A times R to the power of 0? What's R to the power of 0?
1.
What's 1 times A? Okay, so you know the right hand side must equal to A, otherwise you've stuffed up. Or you've stuffed up your left hand side, one or the other. Alright, n to the power of 1, well that becomes A, 1 minus R, over 1 minus R. And then the 1 minus R cancels out, you got A. It's different than before, right?
Yeah.
But don't worry, you just do it. You know a lot of math right now. You don't need to go, okay, this is hard or anything like that. Assume true for n equals k. Okay, so rewrite that the whole thing. Later on, you're going to start seeing me. I won't even write these questions out anymore because they're kind of silly with k's. You can just write it straight away, hey? But anyways, A, 1 minus R, k over 1 minus R. Cool?
Yeah.
Step 3, where you're getting your marks. Prove n equals to k plus 1 is true, pretty much. Okay, so prove true, however you want to do it. for n equals k plus 1. Okay, so we're trying to prove a plus blah, 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 blah. Not interested. AR. Now, k plus 1, take away 1 is k. Right? Into there. Or into n. However you see it. If you're seeing n, then that's it. N. K plus 1, take away 1, you're going to just have k, right?
Yeah.
It's the same as subbing into that. I don't know if you realize. You're subbing in k is k plus 1. Okay? Because k is k plus 1 when n is k. Anyways, whatever. Equals a 1 minus r, but rather than the n that was here before, or the k, it's going to become k plus 1 over 1 minus r. Alright. Let's see how we're going to do this. So, a different color again. Left hand side. Well, that's s of k plus t of k plus 1, right? So s of k, well, that's just a plus ar. You just copy this. A plus ar squared plus dot 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 plus ar k minus 1 plus ar power of k plus the tk plus 1 term. That's that one.
Yeah.
Okay, the k plus 1 term is that one there. That must eventually equal to this. Right hand side. Alright, we can do this. This whole thing becomes that. You agree?
Yeah.
Because obviously it's s of k, right? And that's the s of k. So we've got a 1 minus r to the power of k over 1 minus r. Whoops. That wasn't meant to be big brackets there. So used to the other one. 1 minus r k, and there we go, like that. And then we're going to plus it to a r to the power of. Guess what you're going to try to be doing a lot with? Obviously indices, okay? There's going to be index laws more than anything. Alright. What do you reckon you should do? Look at this. Look at this. So look at this. And look at this.
Common denominator.
Hey, that's not a bad idea, hey? Okay, common denominator. So I'm going to get a 1 minus r to the power of k plus ark 1 minus r over 1 minus r. Look, at least I've got the denominator now. All I'm hoping is that this numerator is the same as that numerator. Well, okay. Maybe the best way to have a look at that is if you had expanded this. Does it say to expand? This is your own personal thing, okay? You want to try to prove it. If you can't see it, maybe this is easier for you. Okay? So maybe you want something like that then, in other words. And by the note, now I saw a lot of people do this. This is not true. 2 times 3 to the power of 2, for example, is not 6 to the power of 2.
Yeah.
They're different bases. You can't do that. And that's a big issue with this topic. With numbers, you're fine. But because you're doing it so much with this topic, a lot of people screw up. So don't do that by accident, okay? Bases must be the same. All right, here we go. A minus ARK plus ARK minus, and then you see R and R, that's going to become plus 1, isn't it? Minus ARK plus 1. Because this is R to the power of K times R, right? You're going to get RK plus 1.
Yeah.
And look, A minus, hey, cancel that out. A minus ARK, I got it. But over 1 minus R, but you're not done. That doesn't prove it's equal to the S of K. You got to write it like that. And that's what the expansion helped with. So then that's A 1 minus R K plus 1 over 1 minus R. And then step 4. True by mathematical induction. Alright?
Yeah.
So can you see how it is the... Okay, so let's have a look at divisibility now. Divisibility is a bit of a different concept compared to what we've already looked at before with the summation ones. And the other reason why that is because you don't have an equal sign. So since you don't have an equal sign, but we kind of do require an equal sign, you're going to see how we're going to actually cheat and we're going to create an equal sign. The good news is the steps don't change at all. So same steps. All we're trying to prove now is that this thing, for any n greater than or equal to 1, is actually going to be divisible by 4. all the time. All right, let's see if it's true. So, step 1. Test true for n equals to 1. So then there's no left-hand side or right-hand side, there's just only one side, right? So 3 times 5 to the power of 1 plus 1. 3 times 5 is?
15.
Plus 1?
16.
16. Is 16 divisible by 4?
Yeah.
Usually I tend to write it. Just write divide by 4 equals to 4. Therefore divisible by 4. That's how I try to do it, because some teachers tend to go, oh, how do we know if you know 16 can divide by 4? So just divide it by 4 and just prove it equals to a whole number.
Yeah.
It has to be a whole number, right? No other number. So divisible by 4. Therefore it's divisible by 4. Alright, done. Step 2. Step 2 is assume, and I'm just going to start cutting it down. Assume n equals to k. Okay, so we're going to have 3 times 5 to the power of k plus 1. Okay, so what? 3 times 5. Okay. What you're going to do here, you're going to introduce this letter m. So you're going to equal to m, where m is any integer. Where m is an integer. Okay? As long as m is an integer, then it's going to be okay. You're not done. 3 times 5 to k plus 1, but you got to write over 4 equals to m. And that's true, right? Look, 3 times 5k plus 1, which is 16 over 4, must equal to a integer.
Yeah.
That's it. Make sense? The reason why we're doing that, because we're about to use this, except we're not going to use it in the way it is now. So you see, you usually see me leave a couple of steps here, a couple of lines, and then write step 3. Reason why? Because this has to still be manipulated for you to sub it into this guy here. Proof. True for n equals to k plus 1. So in other words, I'm trying to, well, there is only one side, so there is no left-hand side, right-hand side, so essentially you're just dealing with this. Cool? Okay, somehow I need to bring this m back, I need to bring this assumption in. Always, you got to bring your assumption in. So you need a 5k, alright? Well then this is what you do. 3 times 5 to the power of k times by 5 plus 1. True or false?
True.
Now what do I know from here? I know that 3 times 5 to the power of k is equal to 4m when I times by 4 and then take away 1. Try and make 3 times 5 to the power of k the subject. That's what I'm going to sub in. That's why we created the m, and that's why we were over 4. So we can actually manipulate.
Yeah.
Okay. And now that's it. You just got to sub in this into this. And then hope that it's divisible by 4. Ready? So then you're going to get 5, which is from here. Just going to put it at the front. And then 4m, take away 1, plus 1. Any questions? Equals 20m, take away 5, plus 1. Equals 20m, take away 4. And then to show it's divisible by 4, try to factorize it. 4, 5m, take away 1. And can you see it's divisible by 4? Because it's obviously times by 4. Which, remember, it's a proof. So imagine we don't know what if you know what anything is. Which is divisible by 4.
So we don't make m the subject.
M is the subject. M has become the subject. Oh, you mean like in terms of m or something? It is in terms of m. You can divide it by 4, and you can prove it's 5m minus 1, but that's not really showing it's divisible by 4.
Yeah.
That just shows us something. What does that mean? No. But this shows us that it can be divided by 4. Can you see if I divide it by 4, it's going to work?
Yeah.
That just shows me a number now. That doesn't look like it's divisible by 4. On its own, does that look divisible by 4? No, but that looks like it's divisible by 4. So usually I tend to leave it here.
Yeah.
But yeah, you don't, yeah. M is just a positive integer, so it's going to be fine. 5 times whatever, take away 1 times by 4 is going to be divisible by 4. That's it. And then step 4, as always. hence true by mi. But again, all you got to do for step 4, it's true for step 3 because it's true for step 2, and since it's true for step 1, therefore it's true for everything.
Yeah.
That's great. N is greater than or equal to 1. By what? By mathematical induction. That's it. All right. A bit of a trickier one for divisibility, just because it's an odd integer. Okay, so let's have a look at this question. Step 1. Test true for n equals 2. If it's odd, n equals 2, it works, right? And it's greater than or equal to 1.
Yeah.
So it's okay. As long as it's equal to 1, it's fine. But if it was n is greater than 1, what's the next odd integer that I have to pick?
3.
Indeed, not 2, okay? Alright, good job. Now, 3 to the power of 1 plus 7 to the power of 1 equals to 10, which is divisible by 10. Alright. Step 2, I get assume n equals to k. So if I'm assuming n equals to k, then I'm going to get 3 to the power of k plus 7 to the power of k. So what? I mean, you're not going to sub that. You can't sub that into step 3. Can you see that already? So you got to divide it by equals to.
N.
But then you got to say something.
Where n is an integer.
Yeah, m must be an integer, right? Because it can't be a fraction. Otherwise, then it's not divisible by 10. Where m is an integer. Step 3. We're trying to prove that n equals to k plus 1 is true. Okay? So, pretty much 3 to the power of k plus 1 plus 7 to the power of k plus 1 is true. That's it. Okay, tricky. No, stop. 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 Okay. Don't get too caught up with that. Go up for a second. It said 4 odd integers. So do I sub in n equals k plus 1? Well, if n equals k plus, if 1 works, what's 1 plus 1?
2.
So that you're telling me 2 should work, but 2 shouldn't work because it said odd integers. So it should be n equals k plus 2. Because what's 1 plus 2? 3. 3 plus 2, 5. And that way you're going to get all odds. Even for if it said even, you still do k plus 2 because 2 plus 2 is going to give you 4. So it's always going to skip the odd or even, depending on the question. That's what I was meant to say. So 3 to the power of k plus 2 plus 7k plus 2. All good?
Yeah.
Okay. Again, I should have left some more room there, but too bad right now. We'll just do it in this color. All right, here we go. So I'm trying to bring this in somehow. But again, you don't know how you're going to bring it in. You don't know what you're going to manipulate, but somehow you're trying to bring this guy in. Okay, let's have a look at how this is broken up first. 3k times 3 squared plus 7k times 7 squared. Okay, well this is 9 and this is 49. They don't really factorize really well. So can you see, regardless, you've got to kind of bring in... All right, here we go. So can you see, regardless of whatever I've got here, there is no way I'm going to be subbing in 3k and 7k in because I'm restricted by 3 squared and 7 squared. So I'm probably going to sub in either 3 to the power of k or 7 to the power of k. Which one do you want to make the subject? Now it's up to you.
3.
Okay, so we're going to make 3 to the power of k the subject. Bear with me. That's going to give me 10m. Take away 7 to the power of k. True or false?
True.
Okay, then this is what it's going to be like. It's going to be like 3 squared, 10m, take away 7 to the power of k, plus 7 to the power of k times 7 squared. Yes, you could use 49 and stuff, but as you're starting to see, we're probably looking for indices, so we probably don't want to do this. Remember, all we want, as long as we can get a 10 factorized out, we're good. We don't care whatever's inside the we don't care whatever's inside the product.
Yeah.
Okay, 3 squared. That's 9. 9 times 10m is 90m. I can do that. There's no, there's no indice there, so 90m. This one, it's not 9 times 7. Don't you dare do that. Right? It's not 9 times 7. It's legitimately, if you want, this is what I would usually write. Here. Take away 9.7k. The sooner you start looking at these questions, the sooner your brain's going to get attached to knowing that you can't do 49 times 7 or 9 times 7. So then in your exam, you won't do that mistake. What's 49 take away 9? Because now, are these the like? Yes, they are. That's the whole point of subbing in, right? Yeah. They're alike, so now I can simplify them. What's 49 take away 9? That's 40, or 49x take away 9x. Yeah, you see it? That's 90m take away 40.7 to the power of k. Probably it's better without indices now that I see it, but just don't multiply in. That's my only worry. Okay. Can you say I can factorize a 10 out?
Yeah.
And I'm done. Which is divisible by 10.
Yeah.
If you did it for n equals k plus 1, it wouldn't have worked. So it only works for odd integers. Step 4, therefore, true by mathematical induction. Okay, now we're going to look at inequalities. Now, before we look at inequalities, I would like to look at, an easier example, one that I've got right here. So we'll write it as 3 to the power of n. We're going to try to prove by mathematical induction that 3 to the power of n is greater than 1 plus 2n for n is greater than 1. Okay, let's use a different color. Just pay attention with this one, okay? Because this one gets funny with the inequalities, and I'm sure that's what you realize. Step 1. Step 1. Let's get back to business. So, we're going to test for what? Test true for n equals to?
2.
You didn't get fooled. N is greater than 1. It doesn't equal to 1. So we're going to prove, or we're going to show that its left-hand side is, what? 3 squared, which equals to 9. Right-hand side equals to 1 plus 2 times 2, which equals to 5. Is 9 greater than 5? True. Again, it's good to just make a little statement. Right? I've done it too much. You can just do the statements from now on. It's good just to talk to us a bit. It's a proof.
Yeah.
All right. Assume true for n equals to k. Well, okay. So that means 3k is greater than 1 plus 2k. That's it. So it's not like your divisibility that you're going to go create something, because you actually have an inequality. That's fantastic. Step 3. We're going to prove true for what?
K plus 2.
No, k plus 1.
Plus 1. Okay.
K plus 2. So, in other words, we're trying to prove that 3 to the power of k plus 1, i.e. 3 to the power of k plus 1 is greater than 1 plus 2k plus 1. Okay, here's where the fun part begins. So let's do the left-hand side. That gives me 3 to the power of k plus 1. That equals 3 to the power of k dot 3. Correct? 3 to the power of k is greater than 1 plus 2k. So then that is greater than, doesn't equal to anymore, is greater than 1 plus 2 to the power of k times 3. That, however, is equal to, 2k. What did I do with, you should have realized that. All right, 1 plus 2k. That is equal to 3 plus 6k. That was equal to 1 plus 2k plus 2. Right? Which becomes 2k plus 3. And can you see 6k plus 3 is going to be greater than 2k plus 3? Which is greater than 2k plus 3. Which is the left hand, which is the right hand side. Or what would be better than that, which is greater than, obviously, what was I meant to write? 1 plus 2k plus 1. I'm going to show you what all this means soon. And then therefore it's true. For n equals to k plus 1. Okay, and then step 4. True by, okay. F9. Let's do this. So we're going to do a harder inequality question now. Same as always. Let's go with purple. Same as always, step 1. True for n equals to 1. 1 plus x. Is it greater than or equal to 1 plus x? N is 1, yeah, 1. Yeah. Is 1 plus x greater than or equal to 1 plus x? Yeah. Well, it's not greater than or equal. Yes, it's equal. So true. So that's step 1. Step 2, like I said, I'm going to do it faster now. Okay, because I think we're up to there that we can do it faster. 1 plus x to the power of k is greater than or equal to 1 plus kx. You're not allowed to do this in your... Okay, good. Let's go. 1 plus x to the power of k is greater than or equal to 1 plus kx. Step 3. We're trying to prove that 1 plus x to the power of k plus 1 is greater than or equal to 1 plus k plus 1 x. Actually, anyways. Alright, here we go. We're going to try to prove this guy is going to be greater than or equal to this. Alright, so left hand side is equal to 1 plus x to the power of k dot 1 plus x. You should already realize that because we've already talked about that. That is greater than or equal to. Alright, I'm going to sub it in. It's greater than or equal to 1 plus kx times 1 plus x. 1 plus kx times 1 plus x. Okay. The expansion of this, if you just want to see it, again, it's all for yourself, is this. We're trying to prove that somehow this is going to be bigger than this. Well, let's see. Let's see if I can expand this. Do I write greater than or equal to or equal to now? If I'm not doing anything, I'm just going to... Equal. Okay, this equals to this. Again, look at the way you read it. This does not equal to this. Where the hell did this come from? It came from our assumption that it's bigger than it. So therefore, it's bigger than or equal to it. That's why we wrote that. Expand this. 1 plus x plus kx plus kx squared. Look, it's exactly the same, except I've got an extra plus kx squared. However, you can't just say because you've got an extra thing that straight away it's going to be bigger than it. That's it. The only reason why it's bigger than this is because no matter what I sub in for x, when it's squared, it's always going to be positive. That's why, because I'm worried, what if it was a negative x value? Because you don't know what x is. K's are your positive integers. X's could have been negative. So if x was a very, very negative small number, so that's a very negative big number, sorry, so like negative 50, and if it was cubed, well then no, maybe that's not going to be bigger than this. Yeah. But because it's squared, yes, it's always going to be bigger because it's going to make it positive, and you're actually going to add it to it. So you got to make arguments like that. What I just did, you have to make an argument. You don't just say because you're adding, yep, it's all good. Which is bigger than 1 plus xk, or bigger than equal to 1 plus xk plus x, since kx squared is going to always be greater than or equal to 0. Pretty much. Okay? So if it's 0, imagine it was 0, well then you're going to get this is greater than or equal to this, which is fantastic. That's what you want. You want equal. For it to be greater than, you want this to be bigger than 0, which means it's going to be bigger than that. That's it. You proved it. Finished. Okay?